So we won't have any questions now. We'll go right into the debate, which is what can ML not do yet? And so can we test the remote connection with Romain Teyssier? Can you hear us? Can we just go back to the Zoom? Hi, Romain.
Can you hear me?
Yeah, we can hear you. And Chiara?
Hello, can you hear me?
Okay. Jens, where are you? Okay, so do we have enough chairs?
Yes, we do.
Yeah, there's only two chairs.
Two chairs.
Yeah. Yeah, so Romain, can you share your slides?
So I have just one plot that I put on the Google Doc.
Yeah, it's best if you share it from your side, because then we can see you.
If I do it myself. Okay, got it.
It's good that they're there just in case something bad happens. But okay.
Okay, can you see it? So
Romain, just we'll just do
1
some
second
introductions.
to give me a chance to make sure everybody knows who we're dealing with. So welcome to the fifth and final debate of this week. Our thoughts are turning towards the future, and thank you, Brice, for a masterful summary of this week and guiding us directly to the questions that we're going to be addressing in this debate already. We have Chiara Ferrari, who's online, Romain Teyssier, and Jasche. And so we'll give all four of the debate participants the chance to state their position, prompt us to start asking questions, and prompt the other panel members for responses. I don't know if there's a particular order in which we should proceed. Okay. I'm being told by the bosses to start with Romain, and who am I to object? So, Romain, go ahead.
okay, can you hear me? I will share my screen once I'm gonna need to show it. But so you're seeing me as a gigantic face, right? Am I right? Okay.
We see multiple giant faces, actually.
Okay, great. Even scarier. Okay, so hi everyone. So my name is Romain Teyssier. I'm actually recently moved to Princeton, and that's my Princeton office that you see here. Actually, I'm in the middle of the 60th birthday conference for David Spergel, so I will have to leave you in less than an hour, I would say. So I want to start first with a disclaimer. So my expertise is on galaxy formation and large-scale structure simulations. So I'm not an expert in machine learning at all. I was probably invited by the organizer because I'm not an expert, so I may have some misconceptions and some naive opinions about machine learning. I'm also a bit skeptical, and so maybe that's why my point of view is interesting, and maybe also my point of view might be wrong. So, okay, I will start with a philosophical concern, and I think it was expressed by the previous speaker quite nicely. So I consider myself as a physicist, and I see my job as trying to find the absolute simplest model to describe nature, with as few equations as possible, as few information content as possible, and I want to test this with experiments, and that's how I define my job as a physicist. And I have maybe the misconception that machine learning is not along those lines, and I think it can be improved, and many ideas have been discussed already. So machine learning, from the outside, it looks like the opposite. It looks like a lot of equations, a lot of convolution operators nested in a vertigo of hierarchical layers, and there is no need to understand what's happening, right? So that's one issue I see with machine learning, and I know there's a lot of work being done precisely on this topic, is the interpretation of these very deep, complex networks, and what can we learn out of it. And I think it was touched upon by the previous speaker already. So the idea is, as a physicist, when I see these machine learning works and papers, I really need to open this black box. I need to understand what's in there, right? Why does it work so well? And maybe we can learn something as a physicist. And I think that's something that is not really the priority of the machine learning papers today, but I'm sure it will become the priority in the future, is the interpretation of these deep networks. Just a stupid example that many people know already, but if machine learning would study the solar system dynamics, maybe machine learning would have been very happy with the epicycles. I mean, we can predict everything to exquisite precision with epicycles, but are you learning something, right? And what is the essence, to use the word that was proposed by the previous speaker, what is the essence of what we learn with machine learning? So that's one concern I have as a physicist. And I know that people are working on these aspects a lot, but it doesn't look like it is the priority just now, right? Maybe for the future. Now, the second point I want to make is about, I would say, optimality. In the context of cosmology, for example, machine learning is used a lot to infer cosmological parameters, and it's very successful in doing so, using convolutional neural network or using simpler techniques, as we just saw. The question is, what is the computational cost of training those networks? Is this somehow optimal? Is this? Are we sure that we are producing, the minimal amount of flops to deliver such cosmological inference capabilities using these neural networks? In the context of global warming, if you tell me that we can train this network by performing millions and millions of simulations, and then have an exquisite precision in the results, is this really optimal? Is this really the best you can do, right? And so, just to show you an example of something that can be used to do cosmological inference is this technique of the emulators. So some people claim that this could be also described as machine learning, but so just to show you this plot, so this is the error, the y-axis is the error that we perform in providing a theoretical emulator of the nonlinear power spectrum, so it requires a lot of simulations. And the x-axis is how many of those simulations you need to perform. And you see that, so forget about the different lines, let's focus on the green line. You see that the more simulation you perform, and here we're talking about 100 simulation, 200 simulation, the maximum was 250. The more simulation you perform, the better the accuracy. And I want also you to look at the y-axis. The accuracy is in percent, right? So with 200 simulation, we can provide a 0.1% accurate emulator for the cosmological matter power spectrum. And then that's the tool you can use to infer what are the cosmological parameters if you use as observable, of course, the cosmological matter power spectrum. So this is really, really good accuracy. This is really high precision and high accuracy. But so my question is, can machine learning do that yet? And at what cost? And here, I want to stress that here we control the cost, that's the x-axis, and this cost is relatively minor, right? And so, that's, and I know that machine learning will make a lot of progress in the near future about that. But my question here is about optimality, right? Are these deep neural nets optimal in terms of, how many simulations you need to perform to train them? And are they also optimal in the error budget they provide. So these are my 2 points, right? So as a physicist, I want to interpret those deep neural nets. I don't want them to remain as black boxes. I want to understand. And 2, especially in the context of cosmology, are we doing something optimal when we use machine learning? And can we control the error, especially when, for future surveys, we want the theoretical error bars to be as small as 0.1%. That's it. I'm done.
Thank you, Romain. Are there any immediate reactions at this point from the other panelists? Go ahead, Jens.
Yeah. So I think machine learning has already demonstrated some benefit, also answering to you, and that's basically we know that these machines have an enormous scalability in solving problems that we couldn't solve before, for analyzing the astronomical images and so on. So we know that it has a benefit. Maybe it had led to indirect detections just by being able to process these enormous amounts, but of course there has not been a direct detection of any thought so far from machine learning. But in terms of that, if we wanted to continue with the increase and abundance of data in the future, we need the scalability. And so this is going to happen sooner or later, that there is basically no way around machine learning. So from that aspect, I think that this is going to stay, not only from whether we are able to reduce error bars or something by the method per se, but just by the sheer workload that these machines can basically address and solve for us.
Okay. Now, I would say, of course, it's interesting to learn to use ML for scalability, but scalability is not a new problem. It's been around for decades, if not more. Before starting the Sloan Digital Sky survey, people were already, there were already some scalability issues and data volume issues and so on. But they got solved without any machine learning. So yeah, that's one way to go. I think there are other ways, and I think usually at the end of the day, that's, for most things, that's not the limitation. I heard many statements before SDSS about how difficult it's going to be to analyze SDSS data because it's so big. But that was not really the main challenge. After all these years. So yeah, that's just my comment on this point. I'm happy to let other people say more first.
Chiara, would you like to comment?
I have no particular comment. As I will say, I'm also a non-expert of machine learning and learning a lot. So in some respects, I join some of the questions of Romain.
I mean, I think this week, a lot of the focus was on pushing the techniques further and what you can do with it. There was maybe less emphasis on parsimony and reducing networks, and some networks were presented with very small numbers of parameters. Some talks had the words zero-shot learning in there, Romain, so that means there was even no training required. There are. I think people are thinking along those lines, but maybe that wasn't the focus of most of the presentations this week. All right. As to keep moving, shall we go to Chiara? Sorry, Brice.
Yes.
Brice next.
Yeah. Brice.
Brice wants to go last. So Chiara.
Okay. I start sharing. And Okay. Can you see the screen, the presentation?
Yes, we can.
Okay. So, as I said, I'm not a machine learner or a machine learning expert. And I will speak about SKO first based on my expertise. I'm working since several years on the SKA, in particular as a director of SKA France. And of course, I'm deeply interested in following progresses in the field, as I think that it will be machine learning and artificial intelligence will be needed for successful use of this amazing observatory. And so in this slide, I presented the usual information about the data part of the SKA. Very often the SKA project is mentioned as the big data project for astronomy in the next few decades, or at least the first one with such extremely big data size. You see there are indicated in this slide the 4 different steps of data processing for the SKA, from the internal brain at the central signal processor that will receive several terabits per second and will produce the visibilities that will then go to the science data processor that will produce hundreds of petabytes of data per year that will need to be sent to the community through SKA regional center. So as you can imagine, there is a huge interest to develop, to understand how machine learning and AI can help in these different steps. And I will try to say what I see as the needs that probably are not yet addressed, using the SKA as an example, since is this kind of prototype of extremely big data instruments. I thought that it could be useful to show some open questions that I have that can be useful also more generally for other projects. What I also would like to mention, and of course I will not enter in details at all, but I thought useful to show the fact that we often hear again about big data with SKA, but I think that what is most important to mention is not only the size of the data, but the fact that there will be many different use of the SKA observatory, many different observing modes. And each of those will require different machine learning uses, developments. And this is something that it's important to mention. The diversity of workflows really is important to be put together with information of the big data. And I think that these two kind of characteristics of future big observational facilities, more than ever, big data and complexity of workflows will definitely be a driving topic for machine learning developments in astronomy. So I think that Michel today gave already an excellent introduction about machine learning for astronomy, at least what is done now. So the aim for me was to try to identify what can be, what we still need to do. And for me, really, when she mentioned the unknown, and when people ask me in which field the SKA is expected to bring a Nobel Prize, I always answer that I hope that I don't know now. And so, but with this kind of complex and big data, searching for the unknown is extremely tricky. So I put together some examples in which machine learning developments are, in my opinion, still needed. I think that the first plot by Kerrigan et al. Is showing some comparison of a capability of machine learning tools, algorithms to detect radio frequency interferences. And without entering in details, I wanted just to show the reference in particular. They are already showing that can outperform non-machine learning methods. But I think that one important point to be mentioned here is that the increasing number of satellite constellations can definitely change the radio frequency interference panorama. And therefore, I really hope that machine learning tools will be able to help us in this challenging time, probably in the radio more than in other bands. Then I have put an example of a fast radio burst, these extremely intriguing and very interesting sources that are definitely helping to do new astrophysics, but also to do cosmology with the measure of the density of baryonic matter in the universe. And I would like to recall that fast radio bursts were discovered a bit by chance by Lorimer in 2007 on data from the Parkes telescopes in 2001. And with the instruments such as the SKA, this will not be possible because, of course, all the data cannot be stored, the raw data. And so looking for rare events, now fast radio bursts are not rare events anymore. Astronomers are observing hundreds of them. But at the time, for several years, it was true that there were more theories about the astrophysical interpretation of fast radio bursts and the number of sources known. So how to look for rare events and unknown sources from such a huge amount of big data, and how to do that not only in terms of the algorithmic development, but also in terms of instrumental computational capacities to do that, to run such huge searches. I mean, honestly, as I said, and not being an expert of the field, this is something that is really puzzling me. And I think that it's something that we need to address together with experts, because if not, we will lose a lot of potential of such a kind of new, wonderful observatories that we will have in hands. And then there is another topic that I wanted to mention that, by the way, Michel already showed quite a lot. That is the source identification and classification mostly. So Michel already showed some nice features discovered by Mercat. That is this wonderful SKA pathfinders in South Africa. And this is an image observed by LOFAR, so at lower frequencies, of an AGN. And basically you see it's the same source. It's written back in time because the central source, the smallest one, the one with the classical morphology of radio galaxies, is the new plasma currently ejected by the central black hole activity. And the more the farther you go, the more you detect extremely strange distribution of radio emitting plasma due to previous activities of the central black hole. And how can you classify this kind of sources? LOFAR, they appear at low frequencies with LOFAR because this kind of old radioplasma is living longer at low frequencies. You can see for longer times at low frequencies, and we are starting to detect this kind of strange beasts. How can you teach to machine learning tools to detect and identify and classify these sources? How to, in the case of thousands of sources of this kind in huge images and so on. So how do we feed machine learning tools. Should we start producing MHD simulations capable of introducing new physics, or through the physics that we know, producing new kind of sources, and then simulate observations and inject those within machine learning tools? I don't know. This is a question that I have, how we can automatically recognize these kind of things. And here, I think that is a slide that I just, I've stolen from a very nice talk of Anna Scaifes, that is a very expert in the field of radio astronomy. She presented very recently at the beginning of September SKEA related developments within AI, in particular for identifying this kind and classifying extragalactic radio sources. And I think that she well summarized what I was trying to show you with this final image. By the way, I put the link to the talk that Anna gave, because I think that it's a nice, very nice overview of some interesting developments and questions. Then I show also these slides with another view of the SKEO data flow. It's exactly the same as before, but just presented in a bit different way and with some more information. As I told you, there are two parts that will be part of the observatory. So for the first time with the SKEO observatory, the computing part will be an essential component of the telescope. It will be at the same level of the antennas, an instrument of the telescope. And there will be two computing parts, the central signal processor and the science data processor that I mentioned before, that will produce the observatory data products. And then all these data will go to a worldwide network of regional data centers that it's out of the
just in the interest of time and allowing the other panel members to respond, could we come towards a conclusion?
Yes, I conclude. So I think that what is important here is to remember that we will need an increase in human resources, but also an increase in infrastructures that will be available to collaborate. And I end with this slide because I heard a lot about the use of AI in astronomy, but I think that what we also need is to see how AI can be used by astronomers to have green data in computing centers, to minimize energy consumption, to minimize downtime, to maximize efficiency. And this is extremely important for two practical reasons. For the reliability in producing scientific data, because we will have better use of data centers if we optimize their all these free initial items, and we will reduce the cost. And of course, we need to be sustainable in astronomy. And so what I would like also to see is how developers of astronomical softwares and algorithms are able to work with the developers of new data centers in order to really work together, not only really on this more technical component. And I think that is something that is definitely very important for SKEO, but not only. And I stop here.
Thank you, Chiara. So do we have any immediate response from the panel members on the issues of extremely large data rates, the recognition of the new in such large data sets, or the integrated view of hardware and software and what that implies? Any of those points? I guess the question for this debate was what can't machine learning do yet, how do these data rates compare with, for example, the types of data rates going through Google, currently going through Google computing centers? Are they comparable, or?
Yes, no, indeed. This is we also often hear that the data rate is even bigger. Of course, then it depends on what you are looking for. So the completely raw data rate is huge. Then they will be immediately reduced, already very close to the antennas. So probably we will share some developments with similar to Google or other big data producers. But what I would like to stress is that in addition to these algorithmic developments, how would we like to develop our technical knowledge in order to be able to run our algorithms efficiently on future machines? This is something that I think that we definitely need to have in mind and to address and to find the best way to work with also with the industry and with other research domains in order to be efficient in running our algorithms and in our observatories.
So, as a question to the panel members, is this a critical issue that what are the platforms that future machine learning is going to run on? Is that how are we as scientists going to have access to those platforms? Beyond the kind of methodological questions.
I may have like a slightly different question. So we were discussing with Karim. So there's so Chiara raised again the issue of the green technology, whether it's like it's going to be ecologically friendly to do machine learning, and Romain as well. But the n-body simulations and running simulations is extremely costly. So probably there is a balance between the two. But if you want to run like I don't know 100 simulations to do machine learning. And the question is whether you're going to need it like 1,000 times afterwards, or do you need these 100 simulations for doing this analysis and you stop there and you're happy? So is machine learning can it not do yet? Is meaning like it's sufficiently green or not sufficiently green, or I mean,
sorry,
okay, to frame it like slightly differently.
Just to precise things in a bit. I was thinking in a bit different way. I was thinking, should we learn more to use machine learning and artificial intelligence to optimize our use of computing infrastructures? Should the astronomical community be more and more involved also from this technological point of view in order to be green? So it's a positive way of thinking about artificial intelligence. It's not at all a criticism for the energy used for running algorithms using machine learning. Just to precise what I wanted to mention.
Any comment on that issue?
Yes, maybe I can add something. So naively, a lot of data-driven sciences are sold. Because there is such a wealth of data that you can actually do a lot by exploring this data, right? And this data is, imagery data, health-related data. So this data is there, whether you like it or not. It's there, and so data science is making the best out of this data. What we do in astronomy is different, right? We generate the data, right? So the data is not there because there is millions of people doing cosmological simulation, for breakfast, right? So we need to generate this data. We need to have simulation campaigns which are targeted and optimized towards training those networks. And so it's a very different philosophical question, right? In one case, you have all this data that is available no matter what, from iPhone, from mobile phones, And in our case, it's different. We're going to generate this data on purpose, right? And so clearly, I know that machine learning has a lot of tools available that can minimize how many simulations you can really you need to reach a target, prediction accuracy. And I think that's great if you can really minimize the amount of simulation you need to do using those tools. But sometimes machine learning in a classical sense, it's not the same. Right? It's more like you have a deluge of data, and then you make the best out of it.
I guess we've seen these sort of two approaches to machine learning. One where we think of the huge amounts of data and the need to go through this, and where we use machine learning as a way to increase the workforce artificially. And then the other approach was just maybe more about the qualitative aspect, both of which were mentioned by Chiara. This just huge data deluge, and on the other hand, the question: how do we use machine learning how do we employ it to actually do better science, to discover new things, to find the unknowns? On the issue of green computing, I guess part of the reason why neural computing has become such a big deal is because it's very well adapted to architectures that are extremely efficient energetically. If you wanted to have the same flop count from that a GPU can provide in terms of traditional computational platform, it would be much more costly energetically. Yes.
Yeah, I'm wondering whether this is something neural networks cannot do yet. So one of the arguments that you just repeated as well is that the idea is to reduce the computing compared to a classical method. But at the same time, we've seen a plot of how the number of papers is going up in a really extraordinary way, and so the number of GPU years that stand behind that is also extremely impressive. And so, and then at the same time, we have that maybe the results that are used in production are still quite limited, right? So maybe one can make the argument to say, well, the computing hasn't reduced, so in 3 ways. One, in terms of computing power spent, it probably increased dramatically. And also in the amount of time people spend in analyzing, so human lifetime. And thirdly, in carbon footprint.
One very efficient neural network architecture are brains, right? They're relatively low energy consumption, high information throughput, and we have now these neuromorphic computers, which computer chips which mimic the brain architecture, which have maybe the potential also to have a large capacity with a relatively low energy requirement. So my question to basically everyone here or connected, is there someone who has experience with neuromorphic computing or has looked into that for maybe telescope data processing or so? Well, he was about green computing and things which neural networks are not doing yet, energy efficient calculation and training. Karim.
So I don't know, but that's Karim actually. I would like to ask another question because from what Brice said, from what you said, Brice, in your concluding remarks, which are really great, there is something which indeed is surprising, that there is no discovery. And here, one of the main things Chiara told us was that we're expecting discoveries thanks to neural networks. So the question I'm asking myself actually is that, is that something that neural network cannot do yet because of them, or because of our data? And that's something I'm really wondering. Is it a limitation of the technique, of the method? It's a tool, it's a hammer, right? We're going to bang, and we're banging with it a lot, as Brice showed us. But do we have enough data, or are we just looking for the right nail to bang on? I mean, that's really one of the questions. I'm sure you'll go back to that, Brice, later. I hope so, at least.
Yeah, I can maybe just say a few things now. Yeah, so to me, the advantage of neural networks is not about big data. It's about complexity. It's about the ability to handle complexity, manipulate complex data, extract information from complex data. What a neural network does is just to approximate a function. That's all. There's nothing else. The problem is that it doesn't tell us how it has approximated the function. The way I think about it, during training, a network, given a task, we have some input data and some labels, let's say, for classification. And given that task, the network is going to invent its own language and vocabulary internally to perform that task. And as we have seen, it can do so very well. The problem is that then it ends up, having this language, but we don't speak that language. We cannot communicate with the network. We don't know what it has learned. And that's quite frustrating, of course, as physicists, because that's what we want to understand. So to me, the key word here is complexity. And what we can do now that we could not do 10 years ago is to handle more complex data sets, more complex data. Now, the point I raised during my summary is astronomical data that complex? And it's a real question, and my view is that we tend to be on the low end of the complexity axis compared to other disciplines, okay? Observations of the Earth from satellites or just pictures of cats and dogs are way more complex than galaxies, okay, galaxy images. So we are seeing lots of papers with machine learning in astronomy, but not that many discoveries. Is it because it's too early? Or is it because actually there is not that much to extract from the higher level of complexity in astronomical data? Is it that it's enough to use our classical statistical tools to basically extract all the key physical trends? And that's it, and ML is not going to make a huge difference. I'm not saying it's not useful, but is it the case that all the low-hanging fruits are reachable without ML? And ML will allow us to basically explore some corners here and there in the data space, but they are just corners. For the main space, is it the case that we can just grab the physics without ML? And I sometimes think that might be the case if I just take the Sloan Digital Sky Survey as an example. It's been studied by lots of human brains for 20 years. Lots of astrophysical results have come out of the analysis of this survey. But now it's been about 5 years. People have used ML techniques on SDSS data, but I have not really seen a new set of trends, correlations, or physical understanding that has emerged from this analysis. So why? Some of the people in the room here, especially the young people, say, oh, but we need a bigger data set to see the actual outcome. I'm very doubtful. Okay, how many millions of galaxies do we need in order to see the actual impact of ML? So if we don't see it today, I don't think there is a guarantee that we are going to see it tomorrow with, let's say, LSST. I'm hopeful, but I just want to say this is based on hope only. Okay.
Chiara has raised the hand.
Yes, so first of all, thanks for the question, because it expressed very well what I wanted to say. And then I have really a question of someone new of the field. Are we not finding something new because we are not looking for something new? Are we using today machine learning to look for something that we expect to find and we teach how to find it? It's just a question, but because I see, I mean, in radio, I think that there will be a big discovery space because it will be an observatory, the SKA, that will allow to go much, much deeper, new frequencies, so it will be a revolution, in my opinion. We already see this with its pathfinders and precursors. But if we keep looking for something that we know already, then we will never find something new. So can it be explained in this way or not at all?
Great. I think this sets us up very nicely for Jens. He can present his slides.
This is not the one. No, but that's my keynote. It's not in the keynote. Yes. Let's. Oh, and by the way, if I can. Okay, I just want to say one little thing here. Sorry to hijack the. No, I just want to say, this is not big data. This is very simple data. This is black and white pixels, okay? But the one on the right is calling for a machine learning technique to be analyzed, okay? Because we don't have the statistical tools to extract the information very easily. We don't need big data for machine learning to have an impact. Okay, so.
Yeah, you have to look on your.
It's on the other.
Oh, on the
screen. Up, down, right, which way is it? Up.
It's on the left.
On the left.
Okay. Okay. And where is?
No.
Where is the?
Lyon.
À droite. Okay. Yeah. I can do French. Okay, that's yours. I think if you.
That's your dog.
So okay. Thanks very much, first of all, for this question, because this question is actually a historic question, and as we mentioned several times during this meeting here, machine learning, or the ideas of machine learning, the concepts are not very new. So this question was actually asked to John von Neumann in 1948 when he gave a presentation in Princeton, and someone in the audience basically just stood up and told him that he does not believe that a machine will ever be able to solve certain human problems that humans can. So this is exactly the same question that we have, and the answer from John von Neumann was basically then, well, if you can specify exactly the thing that it is that a machine should not be able to do, then I can build exactly that machine that's doing exactly that. And that is basically what we have heard here from Ben several times. If you can write down a loss function, then you can have the machine sorting out the rest. And that basically tells us that essentially by pure conceptual ideas, machine learning should be able to sort out a lot of problems. The other things are technical details, but the first problem starts with writing down the loss function. So the first problem starts with writing down a loss function, and that is the human input. So that's where the limitation of the application of machine learning starts right now. And I think the first step is that we basically as a community need to increase the training for our researchers. This means not only technical skills, so they need to become better programmers, but also they need to have a deeper understanding of what machine learning is, statistics, and probably beyond the scope of the typical statistics course that we teach in physics these days. So let me move on to the question on how can we classify things that machines can do maybe already today, and what machines cannot do. right now from a conceptual point of view. I would actually like to use the system from Kahneman, from Daniel Kahneman, that he used in his book in Thinking Fast and Slow. And basically, he separates thinking into types and systems. The system 1 is basically a system where we solve perceptive tasks. It is classification tasks or discriminative models, something like that. So that's basically where we have seen in machine learning major successes so far. So we are very good at classifying cats and dogs. We can apply this to galaxies and so on. So all these tasks that humans do quite intuitively, very quick, and probably also like driving cars fall in this category of system 1. So things that we basically address intuitively. And I have the feeling that's probably the class of problems that we can address with machine learning these days. What probably we cannot address that easily is the system 2, and that's basically reasoning. So have machine learning algorithms that actually reason about the data, and I think that might be interesting for us in the future. And this could be like, we want to have machine learning algorithms that can do some common sense reasoning as we typically do. We would like it to do some causal reasoning. I'm going to talk a bit about that. And something like a self-explainable machine learning algorithm that basically explains itself to us and maybe also explains what the data is actually about, because that's what we want to learn. It should be transparent, and I personally have the feeling that if we just want to have explainable AI and in the terms of Oracle that we can interrogate, then we still have to come up with the questions that we ask. So I would like to have machines that basically try to explain to me what they found in data. And then, of course, something that's also very important for physics or for research in general is hypothesis generation. And these kinds of tasks are cognitive tasks of a higher level, can be still automized, but that's not where machine learning is at the moment. So we had a lot of discussions this week, and I don't want to repeat them. I think most of the discussions that we had were with respect to system 1. So basically detection tasks, regression tasks, and so on. So we have gone through all the points here that we should basically test. We need better uncertainty quantification. We have the problem of interpretability, explainability. Do we have enough representative data to train those machines, or what are known and unknown inductive biases, and the reproducibility? That's an issue in the computer science community. I believe that in principle, apart from practical implementation, this is a kind of systems that we can basically automize, and we probably should do. There's a lot of human potential working on that right now, and in industry and in academia, and I think there will be solutions to these kinds of things. And the other thing is that for these kinds of problems, we can implement a pretty straightforward program. We have discussed that. We can just stress test the methods in order to gain more reliable trust in this. And we heard about the strategy of migration of trust, where we basically start reproducing first results of established methods with machine learning results, and then we can slowly migrate our trust in the machine learning regime. So there seems to be a straightforward way that, at least in principle, we could follow to establish this technology in the future. I would like to talk a little bit, because that's a futuristic outlook. This is something that we cannot do right now, but what we probably would like to do at some point. We would like to have self-explainable machine learning, causal inferences, and so on, and in particular also uncertainty quantification. And I believe that the path through that is probably more through the generative modeling aspect. And we have heard a lot about this generative modeling via GANs or autoencoders, variational autoencoders. So the idea here is that we basically generate many hypotheses that are compatible with our observations through a generator that you could have trained via a GAN or whatever. The idea is basically that you have a latent space in which you basically can generate random noise and then create arbitrary data sets, and we would like to train this, for instance, in the Bayesian setting to represent that these things represent our posterior distributions, and that they can basically be used for tasks like posterior predictive tests. So what is very important, if we want to now learn about physics, then it's very important that we are dealing here with a statistical system. And these data-driven approaches, they are basically associative. So, of course, they learn an association between the latent space and the input data. But I probably can assure you that the way how nature generates dogs is not this one. So if we actually wanted to learn about the underlying physical or natural processes, then we need to have a different kind of reasoning. So this is a clear limitation. This associative learning of these machines will not allow us necessarily to get the insights that we would like to have. I'm going to translate this into a cosmological scenario where we basically have here two processes which yield both the same cosmological power spectrum, but you could take it basically for any endpoint function. On your right, you see the process 2, that's just a Gaussian random field. On the left, you see basically a large-scale structure simulation, and both processes have exactly the same power spectrum, but they're very, very different. The large-scale structure simulation is something, it's a causal physical process that we can understand, where we find reason in how this data was generated, whereas on the Gaussian random process is a pure statistical process with intrinsically very little meaning. What we actually want to do is, maybe for the next generation of science supporting machines, and that's what we have been discussing here as well, is we don't only want to use the associative components that we would get from purely data-driven approaches, but we certainly need to implement some kinds of model aspects of physics in order to also account for causal effects or something else, if we want these machines to provide us with explanations that we can trust in. And that's what we heard from Licha yesterday, getting trustable insights and believable insights into the data and explanations for the cosmological parameters that we infer is very critical to us as humans in order to gain established trust. So that essentially was the original idea for developing the Borg algorithm, because we felt that just statistical associations are not enough. We would like to have a machine that in principle would be able to tell us a causal plausible history that can tell us how the actual universe came into being, or the large-scale structure. And what you basically see here is a formation history of the Sloan Great Wall. So you see that it's a plausible formation history of how the structure has originated, and then we get this more generally for the entire large-scale structure. So we can have a causal history of how the large-scale structure in the universe came into being. And then there's this very nice work from Natalia recently, Natalia Porqueres, Alan showed this as well, that if you use this entire field-based approach, that you actually can get very nice parameter constraint. So what you can see here, that this is a system where you basically get a combination of two things, right? We get the system 1 component, which is fitting cosmological parameters, including uncertainties, plus the system 2 component, which is providing us with an explanation for how this came into being. And that is much, much more explanatory than just a cosmological power spectrum, because there is a causal inference aspect in here. So these are things that are to be considered if we want to really have a machine that's going to tell us about fundamental physics. And there have been many approaches trying to implement physics in those machineries. Here's another work of explainability that you can do. That's work by Natalia Pokars and also Guillaume Lavaux. Is the question, if we have a physics-informed machine, can it maybe tell us what's wrong with the data? Because a typical machine learning algorithm, you train it just to tell cats and dogs, but it will never come back to you and say, I can't tell you because the data is not adequate to answer this question. So in reality, we are facing situations where we have a lot of systematics in the data, and most often the thing we are fighting with is unknown systematics. This is an example here that Guillaume analyzed, where you basically have data contamination that you do not know in the SDSS. It can lead to these excessive large-scale measurements of power in the power spectrum, but if you inform or if you give your machine the freedom that it knows that there could be a component of unknown systematics, I'm not going to go into the technical details, we can discuss that later, but then the physics-informed machine can basically use this information to disentangle what it believes to be a data contamination and the actual physics signal. And that's Guillaume's work, where you basically recover the power spectrum very nicely. But what's more important to us as in this proof of demonstration here is basically that you can then go back and interrogate the machine and ask it, what did you see in the sky that you didn't like in the data? And I don't know, I don't have a laser pointer, right? So
it's the big button in the middle. It's a logical pump, that one.
Okay, so what you can see probably here is that you see these striping features in these things, which are clearly not of a reasonable physics origin. So what the machine did here, basically it reported there's something that I didn't like in the data, please if you think it is a physics signal, follow it up in any case. So this greatly adds to the safety of these kinds of machines. When they are physics informed, they can give you what they didn't like in the data. And I think that's very important for the next generation of galaxy surveys, which are clearly more dominated by systematics and many systematics that we don't know explicitly. There's another thing that is actually an exploratory project that we did with a student from Munich, Andrea Kocic, and he basically asked the questions, can we use this kind of machinery of these causal inferences to ask new questions about the universe? So this is a type of what-if question. So what if the universe would have different cosmological parameters? How would it appear, and where would we see the changes? And you can see that when you do this, then you basically see that for a cosmological parameter question, the infall regions onto the cosmic structures are very relevant to the machine. That by itself is not a very interesting result, so that is actually known quite well. But the fact that you used a quite dumb machine to figure something out that's quite useful and has been reported in literature by humans is quite encouraging, that we might be able to develop machines that are supporting us in building better hypotheses on where to search in the universe for specific questions and learn faster. And actually that is part of that work, that you can basically use this kind of information and the learned information then to ask the question, where in the universe could we optimally retrieve the data for answering specific research questions. In this case, you see a map of the Fisher information, so that's the expected gain if you would observe these different observations. And you could then think that you could build an iterative framework. Basically, you have a machine trying to answer this question, taking data in the specific locations, and you iterate the process, trying to iterate the scientific method. We are far away from that, so these are things that the machines cannot do yet, but that's where I see potential that could be explored and could be very interesting in the future. So I just want to briefly summarize. So I believe that the systems of type 1, simple perceptive tasks, classification tasks, that they are in principle automizable. We can certainly control them. We can implement a program. It will go to take time such that we can use them reliably in scientific applications. We have discussed about that quite a lot. The second part of System 2, that's actually a more futuristic approach, but you can see that we basically could do interesting things there. So we could use these generative causal models to basically give us explanations, much more interesting explanations just than pure associative features in the data. The ultimate goal would be then to have these assistance systems that can help us addressing research questions by finding optimal points in the data or in the sky where we could optimally retrieve the data, in particular if we had specific research questions.
Thank you, Jens, for these new perspectives. So, any reactions from the panelists?
Sorry, if I can start with a naive question about the data contamination. Do you think that the data contamination could be the database for the looking for the unknown?
So what we did in our case is we didn't explicitly tell it what the data contamination is. So we gave it the freedom to completely explore what it is. The machine is informed about the physics of the cosmic large-scale structure. So basically it's informed, it has information on that gravity exists. And it uses this information to ask basically the question, is it plausible that this should be a part of the data that should be interpreted in terms of physics, or is it more plausible that this is actually a artifact in the data? And so it is not informed, we don't make a particularly explicit statement on how these contaminations should look like. We basically fix it at the other end. So we basically use the physics information to find this out. And I think the neat thing here is that you basically get this in explainable thing. It really gives you a map in the sky where you can look for those things even if you don't understand. So you're not as completely blind as if you just had this power spectrum. It tells you, please look into these things, either in your detector or in the sky, there's something going on. This kind of explainability is valuable, I believe.
The question on the Slack, Jenny Wagner asks, AI yielding only, or just one plausible history of cosmic structure formation does not give you an answer whether it is a unique one or how broad the range of solutions is. Using mathematical reasoning, you may get an idea of the degeneracy space. Do you think an AI may also tackle the uniqueness problem in the future, and how important is this to establish trust in AI-based results?
So in general, in this particular case, I should have said that it's basically a posterior distribution. It was one sample from this posterior distribution. So it is actually, we have an entire ensemble of plausible histories. They agree on average, they agree to the degree of the information that one can reliably extract from the data, but they disagree to the extent of the uncertainties in the data. So it is basically exploring an ensemble of possible large-scale structure formation histories that are compatible with the observation. So it's not a unique solution.
Good. Other questions, comments? Brice, are you convinced that we have now discovered something new in Sloan using machine learning?
What is it? No, of course, you know, certainly we are making progress, but my point is that it's really not at the scale of the number of papers and projects and resources put into this.
And there are no neural networks involved in this work.
And in this case, I wanted to say that as well. It's not about neural networks. So I still would like to see a neural network-based discovery. Yeah.
But then would the neural network-based way of looking for places where we could make discovery. Yeah. Is that a complex enough task? Is that the way to use this particular tool in your view?
I mean, it would be good to use them that way, yeah, to tell us where to look and ending up seeing something interesting and something useful for improving our physical understanding. But we are not there yet. Yeah.
Romain, do you have any comments before we ask Brice to conclude?
No, I'm curious about the official interpretation of this systematic effect that we discovered.
I guess you're not the only one.
Yeah, I think we are interested in this as well. I could pass on the question to Guillaume, but I don't think that we have a real explanation for that. That's so far what the machine returned. We didn't do the follow-up investigation, what it actually is. But it could be done in principle, yeah.
No, just a follow-up, but perhaps you'll touch on complexity again. I mean, we've been saying for years that actually computing the large-scale structure and describing it in detail is a complex problem because of this. It's non-linearity. Sorry. So, which is why one of the reasons why we're using NBD simulations, and then we do Bayesian on top of that, and all of that is deemed complex. And your claim is still that this is not complex enough. So, but it's complex when you want to compute it.
Yes,
so
I agree. This is complex. I had a note in one of say that when it comes to large-scale structure, cosmological parameter inference, yes, there is definite progress. We now know how to handle non-Gaussianities. We did not know, or we had different ways to do that and not as good 10 years ago. And there, yeah, but that's parameter inference, and that's in the context of something we can simulate.
Yeah, but still, your claim from your slides for the concluding remark, where like, well, it's complex, but not that complex. A few layers or something which is not even learning anything is more than enough. So, in your view, what are we missing? Where are we making a mistake with your computation? Is the complexity that we see just because we are not using the right formulation, or is it something else?
No, so my point is that we have to be careful using tools that are coming from a different field, a different regime, where the complexity is much higher, and just hoping or assuming that those tools are going to do great things in our world, because we are in a different world and we're at much lower complexity. So of course we can do things, and it's exciting, and all sorts of interesting things will happen, I'm sure. But we have to be careful. It's not a given that just using a CNN that was designed to train cats and dogs or to run on ImageNet will necessarily lead to a new physical understanding in our field. Those are not the same things, and we have not yet seen that happening. So is it just a matter of time? Do we have to just better understand the regimes in which we should apply those tools? Or is it that astronomical data is just not that complex on average?
So maybe in light of the time, let's ask Brice to present his remaining remarks or comments or slides, whatever you have prepared.
Oh, so coming back to the debate, what has ML not done yet? I think my message has been clear. I think ML has not yet done the obvious in astronomy. Which is to generate a whole set of new discoveries to improve our physical understanding of astronomical objects. That remains to be seen. I'm hopeful. I think there is great potential, but we need to think and understand in which corners of our data space those tools are going to have a real impact. And I think this exercise has not happened enough. And we have, during this week, we have seen many very interesting neural net-based techniques rediscovering things we know already. So that's great, but it would be even better to see a wave of discoveries that were not reachable without ML tools. So I'm hoping that between now and the next conference, this is going to happen.
So we have a few minutes for any final questions. Yes, please.
more of a comment than a question. The way I see this explosion of papers and all of the work we're pouring into is more of a self-calibration of our trust for our own abilities. So we are learning how to use these tools as a community, and I think the excitement also comes from the fact that we share this excitement with the industry, and there is, a second pathway for a lot of us. So it's, if you allow me the analogies, like when people see Google Maps for the first time, what do? They look up their house. And they build trust of the neighborhood. Okay, I understand what I see. And then you can go and look at other exotic places in the world. So I think we are there. We're looking inside our house. We are exploring stuff we understand. And in the next 5-10 years, we will have something more interesting coming up because we will learn to ask the right questions in between.
I like the analogy. I would like to say that we have to keep one thing in mind. When we, people here in the room, people online, machine learning users, talk about this, we share the excitement. But that's not the case for everyone in astrophysics. And there is some sort of a divide in the community, and a fair fraction of the community, people who are not using machine learning techniques, are very skeptical. And they might have looked at their own house on Google Maps, but they are not convinced yet, or not at all, that the machine learning wave is doing anything in astronomy, or not much at least. And we have to keep in mind, especially for the younger people in the room here, that when you will apply for jobs later, those people are going to sit on these panels evaluating applications, and those people are not convinced. They don't just want to see ML in the title, they also want to see discoveries and results and physical understanding. And those people are not in the room here, I guess, but that's a fair fraction of the community, and they have a very, very valid point that I completely share. And I think it would be great to have a better balance between the promise of ML and actually what it can deliver in terms of astrophysics.
Maybe another.
If
Chiara has a.
If I can, yes, if I can comment, I'm very quickly, but I'm very. For me, it's very important this comment about young persons, and I remember discussions with the director of WSEG at CERN concerning not machine learning, but computer scientists. We need to integrate also in our domain that if somebody is doing research in machine learning, is research in astrophysics, because if not, there will be, indeed, it will be difficult for them. So it's part, like people that are developing instrumentations or other tools, it's part of research, is doing astrophysics. And I think that this is something that we need to be able to push forward. If not, indeed, we will lose the experts in the field, since industry is looking for this kind of experts. And so it's important that we keep those, the young generation that is formed now, that we keep within our field.
Right. I think it's also it would be wrong to fault people for verifying and developing these techniques and getting a feel for them and understanding them at first before claiming amazing discoveries. So I think that's probably a healthy process. Oh, there's a question back there.
It really comes.
Name, please.
Oh, Lungelautzen. Lungelautzen. My question really comes back to the discussion about whether or not there had been any ML discoveries in the SDSS. Don't you think if ML had been at the stage it is now, that we would have made many of those discoveries over the last 20 years much earlier in the process, and therefore might actually be further along now than we would have been otherwise? Not necessarily because the machine learning could make many more discoveries than we could otherwise, but we might be able to find some of them significantly faster.
Yeah, no, so things would have been different if ML was around a while ago, but to me it's interesting to see that adding ML to the Sloan Digital Sky Survey has not changed anything in terms of understanding galaxy formation and evolution, in terms of understanding the physics of AGNs, the interstellar medium, and etc. So yes, of course, if it was part of the equation back then, it probably would have had a role, but which role, what role, I'm not sure. And adding it to the equation now doesn't seem to make a difference, despite the vastness of the data space provided by the Sloan Digital Sky Survey, combined with all the other data sets at different wavelengths that we have. So I don't think it's a limitation due to the data, and I don't think that just waiting for Euclid data or LSSC data is going to make a big difference.
Thank you. So I want to touch on the point about the skill set.
Could you also state your name, please?
Sorry, I always forget. It's Marko Shuntov. I want to touch about the point raised about the skill set required to do machine learning in astronomy. So do you think we're kind of maybe reaching a bottleneck in terms of how well we can exploit the full potential of machine learning to do our science? Because machine learning is complicated to begin with, and it progresses so fast, and it becomes increasingly more complicated to do and learn how to do. And on the other side, we have astronomy, and which is also a complicated science. And like we need the sufficient skill set in both areas in order to do and advance that our knowledge and exploit the full potential. So do you think the way we're training ourselves, especially the students, is maybe proving is a bottleneck in a way? It doesn't allow us to exploit the full potential, and how do you think we can widen the bottleneck? How would you train the next generations of astrophysicists in the framework of the current university systems, from undergraduate to graduate programs?
Yeah, so
it's a very important, very large question that if anyone has any suggestions, we'd be very grateful for, but probably will not be able to solve tonight.
Yeah, it is true that entering the field now is probably overwhelming. You have to learn at the same time astrophysics and all this. The machine learning techniques, I mean, the issue is that every 3 months there is a new one on the table which does great things. And so it's not, and we don't have textbooks yet. The field, it's too young, and it's changing all the time. So it's very different from learning the more classical statistics that was the only thing we had to learn back then. So yes, it's a challenge for you, but not only for you, for also the more senior people in the field who would like to catch up with machine learning, learn the tools available and so on. It's a real headache because there are no clear starting points, and there are all these new techniques on the table all the time. So it is challenging, not just for you, for myself as well. Just catching up with all the advancements in the field is difficult and time-consuming. So I share your pain. I do not have an easy solution to that. There are some online discussion groups, journal clubs, and so on. I can maybe advertise one that I've organized for now 3 years, the ML Club, mlclub.net. And so every other week, we meet to discuss machine learning techniques with an astro focus. We started last year a series of debates, which was actually the inspiration for the debates we had this week. So personally, I learned a lot by just talking to people and understanding what they learn if they have discovered interesting techniques, because the literature on machine learning is impenetrable. It's so vast. So I do share your struggle. And I wish you good luck.
Yeah, I think that part of the solution is also to develop good taste, because just like any library, you're never going to be able to read all the books in the library, but you go from one good book to the next.
Yeah.
So perhaps in a way of a joke, still on the discovery thing, since we're going to use machine learning no matter what, because the tool is there, it's fantastic. We've seen many applications. Perhaps it's not really the tool we should use, but we're going to use it anyway. So I'm sure that any discovery we will do in the future, we will use machine learning. Whether this was really useful and instrumental to the discovery, I'm not sure. But at least I'm sure that if we have any discovery, machine learning will be part of it.
Yeah, I agree.
It's great. So maybe on this point of agreement and this positive outlook, We look forward to all the amazing things that are still to come, and that machine learning cannot do yet, but hopefully in the future. So let's thank the panelists again for their positions and discussion. And thank you to the audience and people on Slack for all their questions and comments that they contributed. And with this,
I would like to suggest a big round of applause for the organizers of this wonderful conference. Thank you.
People have already asked us to organize another conference, but I'm not sure we're ready to go there just yet, but maybe in a while.
Anyway, so I think it's time to wrap up. Any last thought, Guillaume?
No. It's time for sleeping.
So we're all very tired. So thanks a lot for your participation, the wonderful talks, the fact that you all were on time all the time, which is amazing for a week-long conference. Your passions, because it's tough to do an hybrid meeting, and it went incredibly well. So yeah, thanks a lot, and well, time to close.
Yeah. Thanks very much, and have a safe trip back to wherever you're going to. Yes. Goodbye, remote participants.
Bye-bye. Ciao, ciao.